My name is Alex. I'm going to be presenting today about PCB design guidelines. All right, so first of all, why PCBs for FRC? So here's just a couple examples on why we use PCBs in our team. First of all, to convert ribbon cables to HDMI. For our vision system, we use ORANs, which essentially in order to get cameras hooked up to them that aren't USB, you have to use these really flimsy ribbon cables, and those usually crack and break. So we made a couple PCBs to convert the MIPI signal into an HDMI cord and then back from the HDMI cord into the MIPI signal for the camera. Another thing is power distribution. We've made multiple power boards. One of the most notable ones is the mini PDB, which basically we don't use it as a VRM because it doesn't have like the 5-volt setting, but it distributes 12 volts to around our robot for CAN coders and stuff like that. More accurate sensors. We stopped using the IMU recently, but before it was really great. We had 2 IMUs on one board, and they would talk to our vision system via CAN bus. Another thing is breaking out sensors to MOLXL. So we have the Spartan board, and we have a ton of other boards that break out our sensors to MOLXL so we can wire them directly using the wires we have right now. That just makes it a lot easier. We basically only use 3 connectors right now, which are Farrells, Andersons, and MOLXLs, which just makes it a lot easier for the team. And then CAN terminators. We have CAN terminator boards that connect directly to MOLXL. I've seen other teams soldering terminators and stuff like that, but just having a little probe that you put on top of a MOLXL connector makes it a lot easier for us. And then finally, it was cheaper than doing a lot of other things like improvising stuff. At least before tariffs, PCBs have definitely gotten more expensive and so have parts now that tariffs hit. Okay, so tools of trade. We basically only use KiCad as our EDA tool, which is electronic design automation. We used to use others in the past, but all the time that I've been on the team, which has been around 3 years, we've only used KiCad. So for ordering our PCBs, we basically use JLC PCB and then PCBWay if we end up ordering them built. I found that PCBWay has a way easier manufacturing UI. So that just makes it a lot easier to get PCBs manufactured through PCBWay. From DigiKey, that's where we get most of our parts from, and then sometimes Mauser for electrolytic capacitors that we can't find on DigiKey. And then for libraries, schematics, footprints, 3D models, stuff like that, all those files, we basically solely get them from DigiKey. They have a really easy interface, so you just click on the bottom right corner for the part, and it'll give you all this stuff. All right, so next, schematic design. Cool. Okay, so here's some just basic schematic conventions that we use to make our schematics readable. So for power symbol placement, we always make sure that power is placed facing up and then ground's facing down. So this kind of makes it so you can read up to down, seeing where the power goes, and then eventually gets sunk to ground. For reading order, we also go left to right if it doesn't have to do with power. Like over here for the MIPI to HDMI board, this was the input, and then this was the output. So it kind of go left to right, if that makes sense. And then for value specifications, we're going to use, for capacitors, we're going to use capacitance slash percentage slash max voltage slash packet size, and then you basically change capacitance to resistance or whatever. We don't have those here because these aren't very spec'd components, but for more important components where you need a specific higher max voltage or stuff like that, we'll selectively include this part inside of the reference right here. Cool. So for protection, we use a couple of things to protect our ICs and just our boards in general. One of the most important is decoupling capacitors. So that's going to be this stuff right here. This basically makes it so that if we have a drop in voltage or a spike in voltage, our ICs basically get the same voltage all around. We use basically 1 per VDD pin, and we're going to use 2 for a VDDA pin. For signal integrity, we use TVS diodes. So that's going to be this stuff right here. This does the same with spikes. And then we also use differential pairs instead of single-ended pairs. That kind of makes our signals more redundant, which is better because we've had signal integrity issues in the past with some of our signals. Basically, switching to differential pairs has solved basically all of that. And then lastly, we use reverse voltage protection. I'll get more into that next slide, but that helps us a lot because sometimes we can't see the silk screen and we don't know which one's positive, which one's negative. So we'll kind of do both, and then only one will work. Okay, so moving on to power supply design. We use WeBench for resistor, capacitor, inductor values, like all this stuff, and for choosing the buck boost ICs. This is an example of a power supply that we made taking heavy inspiration from WeBench. We also use reverse voltage. So the WeBench part is going to be like this part right here. We also use reverse polarity protection. So that's going to be this part right here. The reverse voltage protection I talked about earlier. We're going to use a MOSFET right here to make sure that the ground rail has a lower voltage than the VIN rail. And if it doesn't, it just won't let it pass and complete the circuit. We also use LED indicators for reverse voltage. So that's going to be this circuit right here. We usually can't see the silk screen, as I mentioned previously, so having an LED tell us if it's like in the right way with green or not with red is really helpful. And we also use tons of decoupling capacitors on the input and output side. So that's going to be the output side right here, and this is going to be input side. I believe WeBench asked us or recommended us to use probably one on each side for decoupling capacitors, but we put 3 on inside and then 2 on the outside. It just makes the output voltage a lot cleaner. Cool. So for schematic to PCB conversion, there's a lot of stuff you have to consider. First thing is metadata. So once you have your actual part in the PCB, you're going to want to eventually get those parts back into DigiKey. And what we find is the most helpful to do that is using metadata. So we basically put on like this, on the symbols field table, we put manufacturer, manufacturer part number, distributor, distributor part number, and then sometimes a link. And then we'll export this using that right there as a CSV and then import it into DigiKey, and then it'll give us a list with all of our components. So how you're going to do this is you're going to just click on the component you want and then click E and then add all of these fields, or go into the symbol fields table and then check these guys right here, which you're going to have to add, and then put them in manually like that. So for footprint and 3D model sourcing, as I mentioned previously, DigiKey usually has a really good selection. You basically want to click this, and then it'll bring you to multiple like different files, so just choose the one you like the most. It brings you to a selection of like Ultra Librarian, SnapMagic, TraceBarts, stuff like that, and you can choose which of those you like the most. And then for folders, you're going to need, when doing the conversion, you're going to need a .pretty folder to put all of your footprints in. So it's going to be like footprints.pretty. And then you're also going to need a 3D models folder. You can call this basically whatever you want, but we just call it 3D models. No space, obviously. Okay, cool. So moving on to PCB layout fundamentals, we're going to do a couple things. So initial consideration is going to be board size. So first thing we want to do is get the edge cuts layer set up essentially immediately. If you know how big your board needs to be or where the mounting holes are going to be, you basically want to put that into your CAD immediately. This helps later on. For example, this design was molded a lot by the fact that there were holes here, holes here, holes here, and then this kind of had to be an L shape because there was a fan right here. So if we didn't know that, or if we didn't do that first, this whole design would have been kind of skewed. Also, we had this 40-pin header here. Just all of that stuff plays a lot into your design. Otherwise, we would have probably put the power regulation right here or something like that. But just having the edge cuts set up immediately, you can make obviously small tweaks later on. For example, like this right here, there was no constraint making this this like line right here where it is, but we wanted enough space for the ribbon cables coming out of here to go into here. So, you know, if you need just a little bit of extra space, obviously you can move it out, or if you don't need it, you can move it back in. But just having the opportunity to visualize where all your components need to be based on what the outline of your board is going to be really important in your design process. Right, so what fab options are you going to have available? So basically there are 3 main fabrication ways to do. The first one's going to be a soldering iron. So for big pitch components, big pitch SMD components like 0603 and 0402s, if you're experienced, you could basically do those in a soldering iron if you do have the experience. 0402s, I've been soldering for a long, long time, and 0402s are still tricky for me. If you can do those, you should go ahead with it, but I just think that definitely you should go bigger if you can, just because it's easier to do those and also easier to debug bigger components. Also, you want to spend more time debugging your board and less time soldering your board. So if you're using a soldering iron, I recommend 06, 03s. And if you really have the space, then just go 012, 06s on everything. For a hot plate, that's going to be your second option. And essentially what you're going to want to do is you're going to want to put all of your small pitch components on one side. This is an example of a board we soldered using a hot plate. We essentially have everything other than that connector right here on one side. So the benefit to that is we're just going to put the solder paste on, pick and place the components on, put it on the hot plate, and then just because we couldn't fit this in the constraint of the top board right here, this connector, we're just going to solder those on. It's pretty easy. It has very big pitch, as you can see, those 3 blue rectangles. So yeah, that's basically what you're going to want to do for hot plate. And then reflow oven, it gets a little bit more tricky. So for you can do mostly any component on reflow oven, basically every component. But the only thing is you have to put all of the heavy components on one side. So inductors, big capacitors, stuff like that, you all have to put them on one side, because if you don't, then on one side, when one side is reflowing, the other side, they're going to reflow and just fall off. So we want to do the small components first. That way, when you flip them over and you're doing the big components are going to stay on top and just be pushed down by gravity, while the small components, they're being pushed down by gravity, but the solder paste is also like sucking them up so they don't fall. There are going to be times where even small components like 06, 03 capacitors and 012, 06s are going to fall. Maybe if you bump the reflow oven, or they might just fall randomly. So you just want to be prepared for that if you're using a reflow oven. That's why I recommend just putting everything on one side as much as you can, and then if you have any leftover like capacitors or resistors on the other side, just put them there. So for trace and via sizing, here's just a couple standards that we go by. We use essentially 20 mil standard trace. It's going to be around that, and then a 10 mil trace for tighter routing. Basically, it all depends on if you're using a sensitive signal or if you're just doing like power. For power, basically use any trace width that's not going to overheat the trace. But for sensitive signals, I would recommend sticking with one trace width throughout the entire length of it. And then if it needs to be impedance matched, obviously impedance match it. We use up to 50 mils for VIN, but obviously depending on what your VIN is, you can use however thickness you want. We use basically only 12 volts for voltage in, so that works for us. I mean, if you're in higher watt situations than we are, you might want to use thicker traces, but this has worked for us. And obviously use a trace width calculator if you're unsure. I mean, obviously if you have high voltage trace that's such high watt, you probably want to use a trace width calculator to make sure it doesn't overheat. And then via sizing. So via sizing rules are going to be similar to trace sizing. Just we're using different numbers. We tend to have the hole be about half of the size than the copper is. So we're going to usually use like a 15 mil hole and then a 30 mil copper, or a 20 mil hole and then a 40 mil copper. Mil is thousandth of an inch, if you don't know. Cool, okay. So some routing practices. We basically try to use datasheet driven routing. So a lot of ICs, especially the power ones, have a recommended routing for them. We found that not all of them are like looked through. Sometimes you'll have connections that need to be connected on the schematic but aren't actually connected in the data sheet. So you kind of want to improvise, but that's like what we use as like generally where we're placing stuff. You know, if a capacitor needs to be close to an IC or a resistor needs to be close to an IC, like feedback resistors or stuff like that, it's going to show you inside of the data sheet. So you just want to keep that in mind. So for two-layer routing, moving on from that, if you want to do two-layer versus four-layer routing, we'll get more into when you want to use either. But for two-layer routing, you definitely want to keep the bottom layer for a ground pour. This is what we did in this. One thing you're going to see in this board is because of how small it was kind of impossible to do it without breaking that rule. This right here isn't ground, this isn't ground, this isn't ground, this isn't ground. But for the most part, we try to use only ground. From any of these pins, they have a clear shot to any of the other pins. So like for example, if that ground needs to pull from that ground, it can just go like right there. So we definitely don't want to do any like trace that goes straight down the middle or something like that. But for small like rectangles like this for heat dissipation on the switch node or a small trace like this, it shouldn't really be a problem. And then for less complex boards, that's what I would recommend it for. More complex boards, you're probably going to want to do a 4-layer routing. And again, we'll get into that more later on. For 4-layer routing, this kind of opens up what you can do in PCB design a lot more. You have a ground and a power plane in the 2 center planes. For power, you can do 3 volts, you can do 5 volts. A lot of the times, you end up doing a mix of them. There'll be a portion of your IC or a portion of your PCB that needs 5 volts, and a portion of it that needs 3.3 volts, and a portion of it that needs 12 volts, like etc. So you end up mixing them a lot, but most importantly is you're going to have one ground plane. If you want to get into digital and analog ground planes, that's a whole different thing. And then splitting the power plane is okay if different parts of your volts need different voltages. Cool. So one thing I noticed, or one thing that I struggled with when I just started doing PCB design is decoupling capacitor placement. This is how we do it on our team. I didn't think that decoupling capacitors needed to be placed close to the IC initially. I thought they would work for anything, but I think it's pretty important that they are close. Just because if they're not close, it won't be able to draw out the power or take the absorption and power fast enough. So you want to place them basically as close to the IC as you basically can. This can be V out right here and then ground. These are the 2 pins to the IC. So as you can see, they're incredibly close here. And then the courtyard for both is like right there. So they're basically touching. So you're going to want the trace from V out to V out and then ground to ground, or any voltage to voltage. And then you're going to want a via basically right next to it. That kind of helps connect it or like draw power from the rest of the board that might not particularly be on that power plane. So just make sure there's a via next to it, especially if you're using 4-layer routing. You need a via there to connect to your embed ground planes. Cool. So another thing that could happen if you're just getting into via design is tombstoning. So this mostly happens in smaller components, but if one pad is bigger than another, a component can lift. That's because there's an uneven heat transfer. One pad gets hotter than the other pad initially, and then it'll reflow, and then eventually what will happen is because it's reflowing, you'll pull the part in and then kind of tombstone just like this. This will happen if there's a really thick trace on one side and a really thin trace on the other side, because the time it takes to warm those traces up is going to be different for each trace. And this is pretty easily preventable. If you make sure that on small components, traces coming out of opposing pads are the same width, then you're pretty much going to be good. Both pads will heat up at the same time, and then don't worry about this for anything bigger than 0805. That's the biggest I've seen tombstone. 1206 components maybe could, but definitely like those big electrolytic capacitors, they have no way of tombstoning. This just happens because the components are so light. So that's what tombstoning looks like, and this is what good design looks like. Because as you can see on both sides here, the way or how hot they'll get compared to their surrounding environment will be the same for both pads, which means they'll both reflow at generally the same time, which means they won't have the opportunity to kind of tombstone up like that. Okay, so moving on to advanced routing and layer choices. So for impedance matching, basically what you need to do this for is for more complex signals or more sensitive ones. So signals like USB, MIPI, Ethernet, RF signals, they all need to be impedance matched. Signals that you don't really think need to be, a lot of them do need to be. But signals that you might think that they need to be, don't need to be. So definitely search it up when you're routing a signal to see if it needs to be impedance matched. If you search it up, it'll generally tell you what impedance it needs to be matched at, which will come out as an ohm value. Yeah, so use a calculator based on your manufacturer. We use JLC PCB to make most of our boards. So since we're using JLC PCB boards, they know all of the widths of their different layers and stuff like that really well. So you're going to want to put in what impedance you want, which is going to be right there, the type, the layers, all that stuff, your PCB thickness, your inner copper weight. Put in a bunch of parameters, click calculate, and then it'll give you the impedance based on different boards. So for this board right here, you're going to need a 6.15 trace width. But for other boards, you're going to need less or more traces depending on what the different widths of the layers are and stuff like that. Right, so for length matching signals, which is basically the partner to impedance matching, what you're going to want to do is, well, first see if your if your trace needs to be length matched. A lot of high speed, or basically all differential pairs need length matching. Some need more accurate, some need less accurate. Generally, I try to make them all really accurate because it's not that difficult. And then USB and HDMI signals need really, really good length matching, especially if you're running them at a higher baud rate. And then CAN doesn't need to be length matched as well. It is a differential signal, but as you can see on the robot, I mean, not all of the CAN wires are the same length, and it still works out because it's just a little bit slower. So when to use length matching. So middle option is for differential pairs, so that's going to give you something like this. So that's, let's say, in this scenario, these 3 differential pairs, this guy, and this guy, they all need to be the same length, and this guy, for all 3, also have to be the same length. So basically, all 6 of these traces have to be exactly the same length, which is what they are right here. So in order to get something like that, you're going to want to use a combination of these 3 tools. So for this is basically for a single-ended trace. I haven't really ended up using that too much over here. For this, it's going to move both of them. So this wire right here is a lot shorter than these 2. So I put one of these guys right here to kind of make it a little bit longer, and then it'll length matched. Definitely when you're doing length matching, instead of doing everything manually, you can put into KiCad how long you want it to be, and then that'll just make your process a lot easier. This is what you use if you basically have a curve. So if it's straight, you won't use this, but anytime there's a bend in the wire, you're going to want to use this because the outside wire now is longer than the inside wire. So you put one of these just right here, and it'll make both wires the same length, which means that like when the signal is sent from one side, it'll get to the other side at the same time because both sides, I mean, the left side might go faster, but it has a little extra length that it has to go, so the right side has the opportunity to catch up. Cool. So 2 to 4 layer trade-offs. 2 layer is good for for less complex design, where you have a full ground plane at the bottom. A lot of designs can't do this, especially if you have multiple ICs, just because you do a lot of routing. In the designs I've shown previously that have 2 layers, you didn't have to do a lot of routing. There was just a couple of like independent systems, and then there was routing in between them. But if you have a ton of ICs all talking to each other on different buses and stuff like that, that's where you get into 4-layer business. So you want to have all your signals and power on the top. That's where it gets kind of difficult. You have to put power and your signals on the top. Obviously, you can go on the bottom layer for just a little bit, but you basically want your signals and your power on the top. It isn't as good for impedance matching. However, it's still pretty good. And then it is cheaper. It's a lot cheaper. And then it's slightly more debuggable because your inner layers, you don't have inner layers. So essentially, anytime you want to probe any wire, you can take a scalpel and kind of take all the fab layers off and then just probe it like that. For 4 layers, this is kind of more complex. Obviously, there's like 6 layers, 8 layers, keeps on going up to like, I don't even know, a lot. But this is a lot better for more complex PCBs. A lot of our PCBs are 4 layers. I think we even have 1 or 2 6-layer PCBs. So what you want to do with a 4-layer PCB is you're going to have 2 signal layers, one on the top and one on the bottom. And you have 2 power planes, so you're going to have ground and then power. So this is kind of like a good example right here. You have ground and then power here, and then you have top and bottom layer, and then those are obviously signal layers. This is less debuggable because you kind of have layers in here that you can't really probe unless they have a connecting point like right here. It is more expensive, and another thing is you have more via options. If you want to pay a lot of money, you can get vias that go just between the top 2 layers or that don't go to the back, like to the top layer, but they go to every other layer. Like there's a ton of configurations, but you're kind of getting into more complex stuff there, and I'm not sure if KiCad even supports that. Cool. So silkscreen philosophy. Here's a couple things what we include when we're designing our silkscreen after we've made our entire board. So one thing that we found pretty important is reference designators. There are a ton of softwares that will help you pick and place your board manually, but just having reference designators there helps a lot when you're dealing with a big group of people all pick and placing. You'll grab a component and you'll say, okay, this is, let's say, C1, and you'll hand it off to the other person. They'll look for C1, and then they'll place it. Instead of having to have the footprints, like all of the, like the board just pulled up, you can just see it on the silk screen. Another thing that's really important is pin 1 placing. Pin 1 placement. So this is for, like electrolytic capacitors, basically anything that has polarity and that isn't obvious. So for this, there's pin 1 right here for switch 3, or not for switch 3. This is for the connector. But you have a pin 1 right here. It's not really that important though, because it's pretty obvious which way this connector is going to be facing. But for less obvious stuff, it's really important that you have pin 1. That way you don't have to go into the actual PCB design. So values, this is for special occasions. We don't use this that much, but in some scenarios, we'll put like 50 ohm or something like that in case it's maybe interchangeable or something like that. We basically don't really do this anymore. We kind of used to more a couple years ago. We don't do this anymore. Logos. So yeah, we'll put our Spartan 971 logo places. It's just cool. And then test point labels. So I'll get more into test points later on. However, having a test point label is really, really impactful. Being able to, all of this stuff basically goes back to not having to check the PCB every single time you want to do something. So that just making your PCB very user-friendly is kind of what all of this goes back to. Connector correction aids, yeah, like contact face bottom on the MIPI. So when you're plugging this in, you have the, basically what you're going to have is you're going to have the metal part on one side, and then you're going to have the rest of it is just going to be the ribbon cable outer material. So if you want to know which side it goes in, stuff like this is helpful. And then warnings, like sensitive, do not touch, and stuff like that. And also knowing which, if you have two of the same like system on one PCB, being able to know which is which. So this is MIPI to HDMI 1. So if we're debugging this, we could say, all right, our MIPI to HDMI 1 isn't working, but our 2 is. Something like that is just helpful. Not having to ask, is it the left one, is it the right one, which way are you looking at it, stuff like that. Just being able to know. Okay, another thing, how to squeeze silkscreen into bad places. So a lot of the times, we're doing really compact routing, and we're not going to have the space for silkscreen. On a couple boards, we just completely abandoned reference designators just because we didn't have the space for it. But it's important that you do, so here's basically how you do it. So one thing that's important is do not put silkscreen on your pads. For JLC PCB for sure, they'll just take it off. They won't even ask you about it, they'll just take it off. But if you have a manufacturer that doesn't do that, you'll get it on the pad just like this, and then it'll end up being a lot harder to solder. You're gonna need to scrape it off, stuff like that. So this is an example of a bad idea, or not a bad idea, a bad example here. So as you can see here, that little white part is silkscreen. This actually got manufactured and ended up being fine, but if you're not using JLC PCB, other manufacturers might not get rid of it. And then, what else? Yeah, okay, min sizing. We usually use 20 mil by 20 mil tech size, and that usually squeezes in basically anywhere. This is 20 mil compared to 0603 capacitors and resistors here. So it works pretty well for us. I mean, you can go smaller if you want to, but this is about the smallest text that essentially everybody can read. And then for tight spaces, arrows are your friend. Like situations here where we have C4, C3, R1, and R2. For here, we can't put R1 or R2 here because then it'll just get covered up by the capacitor that's right here. So we end up just going like this and then putting a bucket under it and then pointing arrows to right here. And I gave this board, when it was being soldered, I gave it to a couple of new kids, and they were actually able to figure out which one was R1, which one was R2, which one was C4, which one was C3. So just making your design pretty intuitive. Stuff like this too. Sleep, reset, boot. We have 4 buttons here, or 3 buttons here, obviously. So being able to know which one's which and not having to look back into the PCB is just basically really important here. Okay, so designing for debugging. Cool. So test points, this is our IMU, and then this is the board I've been showing the entire time. This is the vision board. So using test points effectively is really important. Lots of components have pads that are too small to probe, so we just use test points. Like, let me give you an example. Right here, these pads are these pins right here are super close. There's no way we could accurately get a probe on one of them. So we basically have a ton of them, ton of the important ones at least, pinned out to test points like this. We don't test point everything, just the things that are important. Definitely signals and then power is important things to test point. And then what else? Small traces to pin out test points, snaking off your main trace. Yeah, so if you have a main trace and you want to put test point on it, essentially what you do is you put the test point pad or hole basically right next to it, and then you'll just have a small trace going out. You don't want to use a big trace or anything that'll impact the impedance of it, so just a small trace should be fine. And then label test points. Over here we have them labeled with what they are, and over here we have them labeled with numbers, and then we'll have a spreadsheet on what they are that we could probably just print out if we're debugging. And then alligator clips for ground. So this is one thing that we implemented pretty recently that's been really helpful. We essentially have a jumper right here, and then once we short that jumper, it's going to make this entire plane right here connected to ground. So when we're using an oscilloscope, we can kind of alligator clip it and then probe all of our points using the alligator clip ground reference. So types of test points, it's best to use test points with components in them. And then if not, use pads that are the largest you have. So what I mean by components in them is there are these components that basically, it's like a rod and then it goes in a circle that you can really easily, with an oscilloscope, you can really easily grab them. But if you're short on space, like here, just use a pad. The largest one that you can use. Here we had really small pads, so when we were test pointing this, you needed a lot more precision. But over here, it was a lot easier to probe all of these guys just because they were a lot bigger. Okay, so spacing, a lot of this is intuitive. For component sizing, you want to keep components as big as you possibly can. Small components are a pain in every way. Having big components is way better, but a lot of the time you are constrained on space, which is why you see a lot of these 06, 03, 04, 02 components in our boards. And then component spacings, it's a good practice to try to spread out components as much as you can. Not as much as you can, just a little bit. If they're too far away, they won't work as effectively anymore. Like situations like decoupling capacitors, you have to have them close. But in other scenarios, you can kind of have them like decently far away to the point where if you end up having to repair the board and swap out a component, you can do that with a soldering iron and not just have to throw the board. In debugging situations, it's very common that you want to probe a specific pattern IC that maybe might not have been pinned out to a test point, and then having a bit of space in between components just makes it so much easier when doing that. If you have questions, leave them in the comments. Thank you.